given by Dr. Gihan Kamel. She's a principal infrared beamline scientist and a team supervisor at SESAME. Dr. Gihan oversaw the construction and currently manages the infrared beamline at SESAME, supporting users in running experiments. She's also actively involved in national and international committees and working groups related to synchrotron science, like the African Light Source Initiatives and many others. The Gihan's talk will be about hands-on at the infrared beamline at SESAME. Please, Gihan, the floor is yours.
Thank you so much, Sana. I just want to make sure that you can see my presentation and hear me in a better tone.
Yes, we can see you.
Thank you. Thank you. So thank you again, Sana, for this nice introduction. And I'm always happy to meet the newcomers for the ICTP SESAME School. I'm always also happy to always speak after Christoph because it gives a lot of like putting the baselines for such a presentation, how it's titled, like hands-on the beamline. So what I'm going to give you today in this presentation, building on what Christoph already shared with you, is some brief information on the beamline, a sort of semi-tour of the beamline, and also some of the applications and, let's say, domains that we are receiving from the users of SESAME. So I go quickly again over some. You will see a lot of potential overlap between my presentation and also Christoph, because this is how the narration of the presentation is better go. So I'm doing about the Fourier transform and for the spectroscopy. It's a vibrational spectroscopy technique, and you can. I'm not sure how many of you already know about the vibrational modes of the infrared, but these are 6 that you see here. And we have to always remember that it's a molecular spectroscopy technique that uses the electromagnetic energy or radiation as physical stimulus. And it's an absorption spectroscopy technique, and it targets the molecules in any material. So the technique that we are handling in the synchrotron is called spectral microscopy or microspectroscopy. You will see it differently mentioned in different terminologies, but basically we are doing spectroscopy with microscopy, and this is how combined together we get one terminology, either spectral microscopy or microspectroscopy. And again, as Christoph mentioned, we have different scales of measuring with infrared. So if I would say millimeter, I would be talking maybe about the conventional infrared spectroscopy. If we are doing microscopy, then we're talking about the microscale. And when we mention nanoscopy, that means we are speaking about the nano scale. I would say through this presentation, you may have also the sense of why synchrotron again shows a superior performance over the globe in special ways, not all the time. Yeah, it depends on the samples and it depends on the measurements. It's not always synchrotron is better than the globar, which we call it globar, as I will show later. So here you will see. I hope that you can get out of these presentations today, these 2 presentations of infrared, of a sense about the technique, a sense on the sample preparation, sense of the data analysis, and sense of the beamlines, how they are employed with synchrotron infrared versus the global or conventional infrared. So what can we get from infrared spectra as a general information? We can get information about the functional groups. Let me put pointer here. So we get information about functional groups, whether presence or absence. It depends on the study that each one of you or us is probing or is interested in. Chemical structure, quantitative analysis. We can also get information about specific conditions. We get information about molecular fingerprint. If you want to compare between different samples, if you want to identify pure samples, And also we can get sort of molecular information without what's called like beam damage or fluorescence effects. With this technique, we can get information basically on the composition of materials. We can get information about the interaction, properties, functions, and also we can get information about the performance, similar to a very famous example now that's becoming a trend when we check the performance of batteries, for example. Also, we get information about the molecular structure sensitivity and how different factors influence the investigation. So you can get information about the order, how molecular structure arrangement and phase of molecular structures in your samples. You get information about the bond conformation, the bond environment, as well as the bond orientation. Of course, there are general applications or general questions for people working with this technique, but there are also very specific questions that some researchers are also considering. We can also get information about the electron energy levels in solid samples, like free electron carriers, like density of states, like band structure. And basically for quantitative analysis techniques, we can get information basically whether semi-quantitative or also qualitative analysis. When it comes to different factors influencing the reaction kinetics of any sample, we can also get information about the temperature, can get temperature influence or temperature effect, the pH, material aging, and also pressure, how it is influencing the reaction rates, especially in gases. I will be touching this later, and also the effect of irradiation on samples. So basically, you can summarize it here. Like if you want to summarize it, you can say that we are exploring the molecular and spectral features of any sample. With qualitative analysis, we get information about the nature of molecular bonds, and we identify the fingerprint, referring to spectral databases and libraries. If you want to go which kind of resolution is targeted at synchrotron, that we go basically with, this is one of the very famous figures or comparison when we compare between the conventional IR, which is basically, as I said, it's a thermal source. It's silicon carbide, for example, and how we call it global source, and the synchrotron. So synchrotron infrared is 1,000 times brighter than conventional blackbody source, and this allows us to probe or to investigate samples in specific conditions. So again, we can use this for diffraction limited spot size for microscopy in very small scale, like 2 to 10 microns. Again, investigating smaller samples, a huge gain in the signal to noise ratio. And we always pay attention. We don't say that we are getting a better signal. We always keep saying better signal to noise ratio. If you look at this example, you can see a comparison between the synchrotron infrared versus the global source. And if you look at, for example, this the red one and the purple one of them, which is the red, is collected by global. And whenever you see 10 by 10 micron square or 10 micron by 10 micron, that is the aperture size of the microscope where we are collecting this spectrum. So if you want to compare between let's say the quality of this spectrum here, the red one and the purple one, clearly you see that at the same aperture, here synchrotron shows you much better signal to noise ratio, while the red one that was collected by global at the same aperture shows you this very noisy spectrum that we will never be using. And again, if you go to 20 by 20 micron square, the blue one, And at the same aperture with synchrotron, you see the very neat, very nice spectrum, the green one with respect to the blue one collected by the glober. So this is kind of comparison that we do regularly to check the performance or the quality of enhancing the signal to noise ratio. This is an example that I always put in my presentations. By the way, many of these slides are repeated many times, but again, for newcomers, it may be beneficial. So this is an example of a mineral sample, just to give you a quick, without any information, without any background, you just compare these two spectra here. So the one that's very noisy here, below here, so this is a spectrum that's collected with the FTIR, the normal, the conventional Glober FTIR. And that's the result of 60,000 scans in 16 hours average. But this one above there, this is a spectrum of the same sample, same conditions, but it's collected with synchrotron. And it's 256 scans only in almost 2 minutes. So this example, even without being expert in any infrared related fields, this example shows you quickly, you can just get information quickly. What's the sort of comparison? What's the superior information that we can get when we use synchrotron infrared compared to the conventional or the lab-based IR? So again, what we want to show here, whether in the presentation of Christoph or my presentation, is that we are going beyond the identification of peaks. So this is a very common spectrum peak assignment. You identify the functional groups based on the wave number or based on the frequency. You identify the vibrational modes, but something we are also doing as synchrotrons, and also I don't want to say that we are doing with synchrotrons because we can also do this kind of mapping or imaging also with the glober. But again, it depends on each experiment and each sample. So we can do the same technique, microspectroscopy or spectral microscopy, also with the glober IR source. So with this, we can do to another modality. Of course, we rely hugely still on the spectra, but we can also do this. It's called chemical mapping or chemical imaging, as I will explain again. So this is, for example, this is visible image of some tissues. And then if we want to understand the distribution, the concentration of specific functional groups or specific vibrations, we are probing specific information that we can relate to the customized maps or tailored maps that we extract from the measurement. This is another example that we also worked on here at SESAME, and it's an experiment. It was an experiment on the specific geological stone structure. It's called stromatolites. I will be also explaining at the end. And with this structure, we wanted to explore just this region. We had this small map of 12 by 20 points X and Y, and this is the result. And with this, as this structure is quite layered, you see the layers here in the visible image here, and here the layers as identified by the IR. So this is quite helpful in many applications. And here with the microspectroscopy, we're also collecting multi-spectra. So researchers or users are more accustomed to the triplicate that we are measuring 3 spectra per point or 3 spectra per sample. But what we can do here is that with the help of the microscope that we are collecting a lot of spectra, and this helps a lot in statistical information or statistical analysis, as well as if we are probing a larger area. So again, we rely on the spectra, and also we look at the images related to the visible. So for example, that was a biological tissue. It was an experiment on breast cancer. So this was a cross-section of a breast tissue biopsy. And you see here, this is the image of this tissue as well. And the one below was tooth cross-section. And again, you see how we see the cross-section under the microscope and the visible objective, and this is how it relates to the infrared features. And again, the sense when you understand that now I want to use synchrotron depends on what you want to see. So if we have this cross section of hair structure, hair has 3 layers. It has the cuticle, which is the outer layer. It has the medulla, which is in the center, and it has the second layer, which is called cortex. So if you want to, for different applications, of course, if you want to monitor the changes or the features of the 3 layers, having a sense that the dimensions of this cross section of the hair is really small. So if you want to use an aperture size like 6 by 6 micron square, that means you need a beam size that can go monitoring the 3 layers of the hair and showing you a nice feature, clean feature, reasonable feature, and a feature that you're going to use. It's not going to show you noise. So if I want to understand or to investigate this cross section of the hair with the conventional IR with the global source, it will be quite messy because it will be a lot of noise. So you are getting noisy data, but with the synchrotron, you can get again higher signal to noise ratio than the one used with the global. Again, if you want to identify the effectiveness of a proper analytical technique, because sometimes you want to, there is nothing called for example, the X-ray fluorescence is better than the IR, or the IR is better than the powder diffraction, or tomography is better than whatever, XAFs or XANIS or whatever. So the point is that what you want to know, first of all, you say, I want to know this, and then you see which technique can serve you better. Like if you want to study atoms and elements, you cannot go to the IR, yeah, because we say that IR, we are working on molecules. Yeah? If you want atoms, you go to X-ray diffraction. If you want elements, you need to use an elemental analysis. You can go to X-ray fluorescence. So it depends on what kind of what kind of information you're looking for, which proper technique that you have to use. And what makes it always nice is that you can combine more than one technique together, because these techniques are complementary to each other. So you can do the same experiment, same samples. Probably you will need just to optimize the sample preparation or sample manipulation, and then measure the same set of samples with infrared or with infrared and XAFs, X-ray diffraction, XAFs, X-ray fluorescence, and IR. And this is something common in the synchrotron facilities. So you can, because the synchrotron facility, you have all these beam lines, you have these techniques, and it's easy for users to combine more than one technique per study. So if you want to get information about a technique that could be effective, that means you need to have a multi-elemental technique which simultaneously detects multiple components in your sample, non-destructive. Yeah, so you need to allow analysis without damaging unique items. For example, if we are dealing with archaeological samples, you cannot just gamble and go for a technique that will produce damage. Yeah, sensitive, that means it can detect trace quantities in an effective way, fast, versatile, and also universal. So you can apply or you can implement or use this technique to various objects, again with minimal pre-treatment, because sometimes we cannot treat the samples. We cannot break an archaeological stone into pieces and then we say, okay, we want to study it. Yeah. So basically, this is a collection of what kind of applications or domains infrared can be used for. So basically, it's a chemistry technique, or it's a chemical method, but we can have applications in so many domains. So in basic science, like physics, chemistry, biology, but also we can have in applied, like life science, pharma, cultural heritage, material science, energy, batteries, archaeology, paleontology, textiles, quality control, industry, whatever you think of, you can be quite sure if everything is controlled, that infrared can give you a valuable information. So here with industry as well, not only for, as I said, not only for basic or like life science or cultural heritage, we can also have a lot of applications in smart materials, energies, batteries, waste management, food industry, water pollution, microplastics, for example, agriculture, as well as electronics. When it comes to the infrared beamline at SESAME, so it is noted as BM02. That means the source for the infrared here in synchrotron is bending magnet. And already Andrea has showed you the machine, the storage ring inside. And I will also show you now this. So BM02 means is the bending magnet number 2 in the storage ring. Yeah. So this beamline was the first new beamline to be built at SESAME with an agreement with the French Synchrotron Soleil, where I met Christophe as well, and we worked together for some time. So I always put it this way: this beamline is a contribution, an important contribution, and it's a joint effort between SESAME and Soleil. It was led by one of the experts of the infrared in the world, Paul Dumas. And if you ever want to understand more about infrared, you have to search for Paul Dumas. So this beamline, as I said, it was the first newly designed beamline at SESAME. Started the design in 2016. So these drawings that you see here represent the beamline design. The fabrication of the components of the beamline was done in France, in one of the French companies. And the pieces were transferred to Jordan. And we started the installation, putting these components together in April 2018. And then in November 2018, the beamline was open to users. So the beamline, as any other beamline, of course, it has different, let's say, activities or initiatives, but it has usually a sort of common opportunities. So basically, which is the core business of any beamline, is to work with users on their proposals, and the proposals are submitted to what we call it call for proposals. It's an announcement. All the users are submitting their proposals. They go to evaluation, technical evaluation, scientific evaluation, and then whoever proposal is accepted, they are allocated what we call beam time. It's a time for experiments. You come with your samples and you do the experiments here. The other thing that beamline scientists are also doing is what we call it in-house research, because we are still scientists, so we also have our own experiments and projects, and this also can go as collaboration, if you want to call it this way. Training fellowships, wherever we have opportunity to train researchers at the beamlines, of course we do that. I'm putting here ICTP because with the ICTP I had the opportunity to train 4 students a few years ago with the full fellowship granted by the ICTP, as well as we are also running national or international projects with the other institutions and synchrotron light sources worldwide. If you want to see the comparison quickly again between the Glober and SRIR, so what you see here, this is the Glober source, so it's like just a thermal source. And this source is emitted in all direction, so it's all directional radiation. It's not focused, it's not collimated. And here it's just a hot filament that when it's heated to a certain temperature, which is whatever, I think with the glower is like 1500 degrees, then it emits the infrared radiation. But again, the brilliance and the brightness of this source, or the brightness of this source, depends on this temperature. So all in all, this source is somehow limited, yeah? But if you want to go further, you go to synchrotron to see what the glober is not allowing you to see. So the first thing is that if you want to do IR, you check if your experiment, if your samples can be done with the glober. If not, then this is when you say that, okay, now I need synchrotron IR. Of course, for some samples, it's quite clear from the beginning that you need to go to synchrotron because it's useless to go with the glober with them. But again, for the synchrotron infrared, the production of this radiation comes from the relativistic acceleration of charged particles, that's the electrons, in this case. And different factors are influencing this. For example, here for the synchrotron infrared, the beam current in the machine, it influences the brightness. And also here, the flux characteristics. This radiation is emitted, you see here, it's coming throughout the storage ring in well-defined tangential cones. So this radiation is well-defined, well-collimated, and well-focused. So if you want to also get some information about the unique properties of synchrotron radiation, you will see some of them are here. So you see here that it's a broadband, the brightness, provides linear circular polarization, pulsed emission. And for us here, we are relying on the brightness, brilliance. And for us also, this is, let's say that these are three pillars that we are concerned of when we work on the infrared synchrotron radiation for spectroscopy or microscopy. So we are aiming at high spatial resolution, better signal to noise ratio, and also faster data collection. Any beamline has what's called beamline parameters. And with the beamline parameters, you will see a collection, or let's say a mix between the machine parameters, the storage ring parameters. So you see the circumference. You see here, for example, the machine energy. We are operating at 2.5 giga-electron volt. Our top current is 400 milliampere, and so on. So here you will see some parameters of the machine, and then you will see some parameters of the beamline. And depending on what we call it collection angle, which is for our case, it's 39 by 15. So what we have here is a vertical collection angle of 15 milliradian, and for the horizontal collection angle, we have 39 milliradian. This depends a lot also on the mechanical constraints of the storage ring, how far we can extract infrared from such facility, because basically the synchrotrons are basically X-rays facilities, and infrared has to be uniquely designed in order to be able to extract infrared. So what we are collecting here, the standard bending magnet radiation, and also the edge radiation. And I recall that maybe Andrea also mentioned this in his presentation, in his tour. Again, some of the regular tests that we do to monitor the performance of the synchrotron infrared beamline with respect to the glober, which is quite the same, it doesn't change, is that something like this. So this is called like single beam transmitted here through 10 by 10 micron square at, for example, with 265 coax scans, resolution 8 centimeter minus 1 for both the synchrotron and the glober. So you see here, this is the synchrotron, the red one, and the glober here is the blue one. And here it's quite, I would say, quite visible, quite valid to see the comparison between the signal obtained by the synchrotron IR with respect to the glober. Again, at the same current, the same aperture size, because whenever you want to compare, you have to you maintain the same parameters, the same conditions for your comparison to be valid, okay? And this is again a particular figure that again you see it for almost all our beamlines. You see a comparison between the signal that you are getting with respect to the aperture size. So if you are comparing the synchrotron, which is red, to the glober, which is blue, you see here, if I have an aperture size of 10 by 10 micron square, 10, 15, 20, this is the aperture size. So this is where I assign this aperture at the microscope. So I close the aperture, I say, okay, I want this size, like 20 by 20, 10 by 10, 5 by 5, and so on. So if I start with 10, 15, 20, 25, for example, I go to 70, 80, 100, yeah? You always see that at the large apertures, the synchrotron and the glober are almost comparable. And sometimes if I see something like this, I automatically go to the glober, yeah, because it gives better condition than when I go to the synchrotron with this, because it's already useless, yeah. And then if I try to decrease the aperture size, if I go to 50, 45, 40, 35, 25, you start seeing the glober disappearing. Yeah, it's getting by time or by aperture size, it gets less and less and less and less. So let's put it this way, wherever you go to lower apertures, this is the power of the synchrotron. So this is where the synchrotron appears to be more powerful. And if you don't mind, if your samples or your experiment does not require to go to this small aperture size, you directly go to the glober, yeah? And always remember that the technique is the same technique. It's microspectroscopy with the glober, it's microspectroscopy with synchrotron. It depends on this, on the resolution, the information, the size, and heterogeneity of the samples, and so on. And this is another very important test that we also do, which is a test to check the noise level of the samples. So, sorry, of the two sources, the glober and the synchrotron. So the blue one is the glober noise RMS, which is in this situation, in this figure, in this test, was 4.2%. But the red one here is the noise level for the synchrotron IR, which is 0.6%. Of course, these numbers are not fixed. It depends on the test, depends on the signal, depends on the aperture, it depends on the current, and so on. So if you look at the blue one, which is full of noise, and you look at the red one here, this is the synchrotron. And imagine that for example, if you are studying, for example, biological sample, if you are concerned of, for example, the protein bands or the amide 1, amide 2 bands, they are here. Yeah. So your bands or your information are here, which is a fingerprint region of the infrared, is full of noise. So your features, if they are there, they will be already masked by the noise. They will be under the noise. And there is no way here to say if these features are there or if they are not, because whatever you see is always noise. But with a clean, let's say, neat noise level with the synchrotron, you will be sure if this is featured or if it's not, if it's there, if it's absent, and so on. So this is very important feature of the synchrotron and the glober, and this is how we call it, again, signal to noise ratio. Yeah, wherever you want to see your peaks, you have to go to synchrotron, because synchrotron is giving you higher signal to noise ratio. That means less noise compared to signal. Another station that we have here at SESAME at the IR Beamline, because initially we had this end station, which is Thermo Fisher end station, spectrometer and microscope. But when we got the new one, which is Bruker one, as Andrea showed you in the tour, I will also show you now. The globe here means that this end station or this instrument is only working with the glober. It's because it's not connected to the synchrotron. Yeah. Then what you have here is a set of capabilities that even when this end station is working only with the glober, still it provides a lot of important and beneficial opportunities. So with this end station, we can do fluorescence illuminations. We can do differential interference contrast. So it's providing extra capabilities that somehow compensate the lack of the synchrotron. Some capabilities that we are also trying to do now, because I said that this beamline started operation in November 2018. That was the first year of the operation of the first two beamlines at SESAME, the XAF X-ray fluorescence and the IR. However, we are moving somehow based on the user's demands. So we see let's say we are securing the basic accessories, the basic approach for such experiments, but we are also trying to move ahead, move forward, expanding the capabilities of the beamline with experienced users. So two things that we are trying to do now is that we're having this thing, which is a monolayer grazing angle specular reflectance accessory, which is this one. This helps a lot to study in situ if there are monolayers, if you are having a material that you want to study the properties and the function of this material being deposited as films at air-water interface or at air-liquid interface. So this is a very nice way if you want to measure thin films, for example, on solid reflective surface and so on. So this is kind of accessory that we connect to the spectrometer and we do the proper measurement. Another capability that is polarization modulation infrared is just with a single box like this one, we can build different optical systems that can be used for different experiments. So with this box, for example, we can do the IRAS, which is infrared reflection absorption spectroscopy. We can do what's called the VLD, vibrational linear dichroism. We can do the DIRLD, which is dynamic infrared linear dichroism. So with just one box, playing with the components, which are basically sample holders, detectors, some rails to move these optical components, mirrors, and so on. You can build your own experiment, connecting it to the spectrometer with the synchrotron. And we started this thing for the first time here at the Beamline last September with a Turkish group. And you see here, this is the box, but you see here, this is how we built the components. Here you see again some mirrors, and so let me show you how it goes. So the synchrotron comes from here to the spectrometer. It goes here to this box, passing by the optical elements and then by the sample, and then it goes back to the detector. Yeah, so there is a specific pathway, which is, you see it here. So the beam comes from the spectrometer, synchrotron, goes to this mirror here, goes to the samples. This is sample holder with some samples on, and then goes to another parabolic mirror for focusing, and then goes to this mirror here, back to the spectrometer, then to the detector. So this is very, let's say it's a very customized and sensitive experiment, but we do these things based on demands from our users and also based on the availability of such optical components. So here we studied some self-assembled monolayers. The nice thing here is this sample holder was fabricated by 3D printer, and we were like changing the sample by whatever we want to measure. So we go to this sample, then this sample, then that sample, and so on and so on. We were moving it with a Bluetooth application on the mobile phone of the user. So you see, it's a sort of you adapt to what you want to do. If you want to know more about this experiment, you can also go to the website and you will find it there. And this is the, as I said, the monolayer bruising angle specular reflectance accessory if you want to study thin films deposited at air-liquid interface. And under consideration, because also we started to have the, how to say, demands from the users like temperature cell, pressure cell, and as well as gas cell. So we are also moving into in situ and in operando measurements. There are a lot of accessories, like we call them manipulation, not really preparation for in our case. But here you see we have for this, for example, this is the regular KBR pellet. This is a liquid cell for measuring liquids. This is diamond compression cell, 2 diamond windows. We put a sample, compress, and these are the micro ATR for the microscope. And this is the specular reflection, and this is cryomicrotone for cross section. So what we are offering here again, we are working on the mid-IR region, 2.5 to 25 microns, and we are collecting part of the far infrared as well. Beamline, I go quickly now. So the beamline typical, let's say, schematic layout is starting with the beamline, with the extraction of the infrared, and then optical matching, and then you go to the hutch where you see the end station and where you do your experiments. So beamline means optical components, means vacuum components, motion system control, and end station where we do the experiments. So here you see the extraction and the focusing. Those are the components behind the shielding wall. So these are the parts of the beamline in the storage ring. And these are the parts of the beamline out, and this is the end station. This is a top view of the bending magnet, the red one, where the IR is being extracted, and it propagates through the shielding wall here to outside. And these are, let's say that this is the heart of the beamline. So this is M1. Let me go to the video. So I hope that you can see the video as I am propagating with it. So these are the components of the storage ring. Here you see different magnets, or there is quadrupoles, sextupoles. I think Andrea explained this. This is the bending magnet, dipole. So this is the dipole, and this is the source of the infrared radiation here at SESAME. And then where the beam is moving through the chamber, and then here, this is called the photon shutter. So it's on and off, or open and closed. If it's open, it means the IR is coming to the end station. If it's closed, it means no IR is coming. Yeah. So this is like the key. This is the first mirror manipulator where we extract. So this mirror is the one that reflects the IR, visible and visible light, to us outside for the end station. And behind it, there is the copper block where the X-rays are passing through a slot in the mirror and then absorbed by this copper block. Then the beam comes here. This is called M1, M2 transfer pipe because here there is another mirror. And just for you to know that this beamline is compact, short, but it's full of mirrors. Each mirror has different geometry, different function, different properties. So this M2 is toroidal. It reflects the beam to a mirror here up there, which is flat mirror. And this mirror here takes the beam outside to the beamline hutch. So what you see here, this is the visible beam, visible synchrotron and the termination of the beamline. And with it, there is also the infrared. So it's coming from here. So without synchrotron, we are operating with global source, which is this thermal source. It's here. And then if we are using synchrotron, it means we're getting synchrotron from here, from the accelerator, pass to the spectrometer, to the microscope, which allows us also to work with different modalities than the spectrometer alone, because with the spectrometer alone, we are just working with transmission. We cannot work with reflection because we have to ensure the sample giving a signal to the detector. But with the microscope, we put the sample here on this micro stage, and we are able to work in transmission or reflection, depends on many factors. So this is called Beamline article. You can go back to it and check. So again, for an experiment with IR, you have to deal with many things like sample prep, sampling modes, transmission, reflection, ATR, whatever, data acquisition, as well as the processing and analysis. So here I put this slide for you. If you can go back to it later, this is what we call workflow, or I call it workflow. So you have to pass by all these blocks. So for sample collection, preparation, your sample can be powder, liquid, or dry, thin film, can be cross-section, can be bulk, fragment. Sampling mode and substrate choice means you are working in transmission on reflection. Transmission means you have to put your samples on any of the IR transmission windows, and for reflection, it's the same. Data acquisition, either you are doing like point spectroscopy, mapping, or imaging, and again, for spectral data processing or analysis, it depends on what you need to know further. So I put here a few information that you can go back to it. Already Christoph explained them. But for the detectors, just want to highlight one of the major advances that we just got last October. That is called focal planar ray detector, FPA, and it's one of the very advanced detectors. The usual detector is single point detector, so we go one point by point. It's long data acquisition. For the FP detector, it depends on the number of pixels, how many points or how many detectors. So it's 64 by 64 pixels, the one that we have. And you can capture above 5,000 spectra in a single shot as a camera, because it works basically as a camera. And here you see the beam, the detector, and these are some examples of the testing samples that we just used for testing the detector. Again, for the data processing and analysis, there are different methods you can get custom to if you want. So derivatives or curve fitting, chemical mapping, multivariate statistical analysis. I put here again a workflow for the data acquisition, spectral preprocessing. And again, everything is somehow, you need to go like a systematic way in the experiment. Usually, we also rely on this if you want to identify some function groups. And for peak assignment, there are a lot of tables that you can refer to identify the peaks in your sample. These are few slides I put here to let you know that it's very sensitive to how you deal with your samples, whether at the stage of the processing or the pre-processing, before going to the data analysis and interpretation. Everything you do, everything you move, everything you do will be affecting the end product, let's say, the outcome of your experiment, which is the results. So you can go back to this. I just put here some of the methods that we are commonly used for baseline, for smoothing, for derivative, and just be sure what you are doing, because any difference here will take you somewhere else. Yeah, this is curve fitting or deconvolution methods, and this is the multivariate statistical analysis. Here we do, for example, this is an example of hierarchical cluster analysis, or the principal component analysis, the PCA, which is a very nice way to get information about similarities or differences between samples. For the software, we have a set of commercial software, but there are also free software that you can use. However, whoever wants to use this software at SESAME, we can also guarantee them access or remote access upon authorization. I take you quickly now to some examples in the last minutes of this presentation. So, for example, we had a lot of experiments on life science. This was an experiment on placenta and plasma for the preeclampsia disease. That was also, so this one, we studied the placenta tissues. Here we studied the plasma of the blood in this investigation of preeclampsia. We also had experiments on breast cancer. We had a lot of experiments on cancer, breast cancer, brain cancer, skin cancer. I don't remember what else, but yeah, we had a lot of diseases that we investigated here, like Alzheimer also, diabetes or diabetic foot, wound healing, Parkinson, multiple sclerosis. So we have a lot of this. This was also on anti-cancer or anti-inflammatory activity of some nanoparticles. This was on regenerative medicine, working basically on collagen structures. And here you see a series of publications on the same application with the same group. This was to also work on collagen biomaterial inks for 3D bioprinting applications. Green plastics, converting the grocery waste to bioplastics. Again, in dentistry, this is dental enamel investigation or mapping with this kind of disease called MIH, and it's disease that occurring only to children. On ticks, also we worked on trying to understand differences between different tissues like salivary glands and gut tissues of ticks. A lot of cultural heritage archaeological. So, for example, 16th century Ottoman tile from the rock, Dome of the Rock in Jerusalem that was used from UK and United Arab Emirates. You see a lot of collaborations here. This was wall painting also, like try to investigate the effect of some polymeric material on these wall paintings. Wood medallion, photographic glass plates, mummies and mummification materials, human remains a lot, human hair, teeth, bones. This was also on mummified skin tissue. This was hair, ancient hair of 2000 years old from the Roman period. This was one of our last publications on textiles, on wool, a historical wool. This is the 3.5 billion years old stromatolites. And again, fossil, like I would say, this is a sort of paleontology also examples. In Morocco, this is skin, ancient skin from Turkey. This is for human remains also for 3,500 years old. Human remains differentiating between non-adult and adult. And I'm happy just to share with you that I have Yuko Miauchi. She's postdoc. She's here with me in the office listening to this. So Yuko started as a user and now she's also working as a postdoc at the Beamline. Also, a lot of investigations on Petra wall paintings, and this is one of our last experiments on pre-Neolithic inhabitants and artifacts, so like bones, pottery, and glass. That is really ancient. If I remember, it was like 15,000 years old or something. And again, a lot of manuscripts studying the paper, like the manuscripts themselves, as well as the ink that's used to write this. So all in all, this is just a brief about the technique. It's non-destructive. We combine the spatial resolution together with the chemical sensitivity of the spectrometer and microscope and also synchrotron, signal-to-noise ratio that cannot be achieved by conventional sources, the microscopic scale that we are really doing a lot of experiments and getting a lot of information still in the mid-IR region, industrial applications, and again, you have to pay attention to when you need to use the microspectroscopy. There are a lot of people I'd like to thank, of course, this you see here, and I thank you so much for your attention. And if you have any question, you put it in the chat. I will make sure to reply to it now. And I think, Just a moment, I wanted to also to show you that this is my email address. I will put it also in the chat. If you have any question that you couldn't ask today, or if I couldn't answer today, you can send me an email. Thank you so much.
Thank you so much, Gihan, for the wonderful talk. We have some questions on the chat, and I will start to reading them. First question says, does the polarization allow you to address particular vibration, rotation, translation modes?
Well, it depends because we had only, I also, as I said this, we didn't do it for, we did it only for one experiment. Yeah. And yes, we were able to monitor some changes for the orientation with this. But again, it's not, I would say it's not a kind of experiments that we usually receive from our users and based on the proposals we receive.
Okay, the second question says, what is the minimum thickness as the FTIR can detect in the thin film?
If I understand the question, so it's minimum thickness for transmission measurements, and it actually depends on the sample itself. For example, when we section biological tissues, we can go down to 5 micron thickness, 8 micron. It depends. Sometimes the 8 micron is really thick. Sometimes it's okay. So it depends on the structure of the tissue itself. And I just give a quick example of the bones tissues. If we want to section bone samples, 5 microns is very thick. And I remember we had an experiment on cross sections of bones. Also I asked Christophe at that time because they had a similar experience at Soleil. And I got to know from Christophe that the thickness has to be in the order of 2 microns to be able to consider it as transmission and to get non-saturated signal. Otherwise, you get a lot of saturation. So the thickness really depends on minimum thickness, depends also on the sample itself, I would say.
Yeah, correct. Is the spectrometer equipped with angular resolution to probe phonon and polariton dispersion in solids?
This is not actually to, I don't understand what does it mean, angular resolution here, probing phonons, but I think this is something that goes mostly to the accessory that we are using to investigate these in the solids, not the spectrometer itself. Or maybe there's an accessory that we fit with the spectrometer to allow this. I'm not really sure of that.
Yes, maybe can Zakaria write again the question,
Yeah,
your
I
answer.
will.
So another question says, can synchrotron FTR be used to analyze inorganic material?
Yes, inorganic, organic, yeah.
Okay, many thanks. A lot of congratulations. Excellent.
Do you want me to
I'm looking for more questions. Okay, another question. What are opportunities to get short-term training at your ER lab?
to get what? I'm sorry, I didn't hear.
To get a training at the
Training.
online
Yeah.
lab.
Well, we have different opportunities. So let me tell you about the most useful, not in the sense of useful, because there is this project is called LAMP. Because we ourselves, we do not have enough funding for training unless we are dealing with EU projects, for example, or other international projects. So there are a major project called Sunstone. I will write it in the chat. So you go to the portal of the Sunstone because Sunstone is a project of training researchers at SESAME, and you can get full funding for that. There is another opportunity for another initiative that I'm also working with. It's called LAMP. So this lab can provide what is called faculty fast team, which is a faculty team member, like a supervisor together with master or PhD students. So it's supervisor with a student, master or PhD. They are to be trained at the Beamline for 2 months. So they get a full funded fellowship for 2 months at any synchrotron facility. Actually, it's not only at SESAME. SESAME is a partner of LAM, but you can have this opportunity at any synchrotron light source. So without project or fellowship, it's quite difficult to obtain a funded training at SESAME. Rather than that, we are always happy to train researchers and scientists when they come to us, of course.
Thank you, Gihan. Maybe I will put in the chat the link to LAMP.
Yeah,
I think it's
lab,
a past,
I
but
will,
I'm sure there will
yeah,
be many others in the future.
yeah, I will also put Sunstone, lamp. ICTP also, sometimes they also provide fellowships, and I think also IAA. So I will put some links in the chat where you can just monitor and check. Yeah.
Yes, perfect. Thank you so
Thank
much.
you. Thank you. Thank you.
So our final talk for this session is by Dr. Alessandro Migliori, currently at the International Atomic Energy Agency in the Nuclear Science and Instrumentation Laboratory. Mr. Alessandro specialized in X-ray fluorescence, XRF techniques applied in environmental studies.